deploying.
Hi, we are Team UC San Diego competing in this year's Design Build Fly competition with our plane, the Orca. Our team consists of many dedicated undergraduate students who are either studying aerospace engineering or have an interest in aeronautics. For this year's AIAA competition, the two main design challenges are releasing, towing, and retracting an aerial sensor probe while in flight, and also lifting heavy cargo containers simulating multiple stored sensor probes. More points are awarded to the heavier and larger sensor probe that can be carried, but the sensor dimensions affect 1. How long of a tether must be used while towing, and 2. The dimensions of the cargo containers for the heavy lift mission. In order for us to determine an airplane configuration, we performed a sensitivity analysis to determine the optimal size and number of sensors to carry for the two missions of the competition. From the sensitivity analysis, we were able to determine the sensor size, weight, and number of sensors to be carried to hopefully give us the best score possible. What we came up with was a high wing configuration airplane with a T-tail stabilizer and twin wing-mounted motors. Aerodynamic stability was a large consideration in the airplane design, and we wanted to build in as much inherent stability as possible for the sensor towing flight. The twin motors have counter-rotating propellers to eliminate torque roll, and the wing-mounted design ensures constant airflow over our main wing during slow-speed maneuvers. The T-tail in the back helps bring the horizontal stabilizer above and outside the large turbulent airflow generated by both the prop wash and the large fuselage needed to store our cargo. Some important final dimensions of the plane include a 5-foot wingspan, 12-inch root cord, 14-inch tall vertical stabilizer, 24-inch long horizontal stabilizer, and a 62-inch long fuselage. The wings are made out of vacuum bag carbon weave 65 grams per square meter fabric with an internal carbon spar running through the quarter cord for reinforcement. The fuselage is made out of a fiberglass foam body that was hand-shaped and hand-glassed. For propulsions, we are using two Cobra CM4515/18 multi-rotor motors with 435 kV ratings. These motors are hooked up to two 80-amp FreeSky Neuron ESCs, which are then powered by either one or two Glacier 4500 mAh 6-cell 22.2-volt LiPo batteries. When towing the sensor, the mission is also a long-endurance flight, which is when we use two batteries. Otherwise, the plane can fly with only one 4500 6-cell battery to save weight. We selected the power system by using data provided by motor manufacturers and compiling everything into a MATLAB script that would calculate the efficiencies using each motor and prop combination to come up with the best solution. That allowed us to swap out the propellers for each mission, which is acceptable in the rules, for the best performance. During sensor towing, we fly with two 13 by 10-inch counter-rotating propellers for maximum speed and efficiency. Our final design can fit 10 cargo containers and can tow a 1.75-inch diameter, 26-inch long sensor that weighs half a pound. In order to release and retract the sensor mid-flight, we opted for a dual-spool mechanism that is powered by two NEMA stepper motors. The signal, power, and ground wires run through the two spools, allowing for signal to be sent from the aircraft to the sensor, following the rules of the competition. To ensure that the cables remain untangled, guide sleds, driven by the second stepper motor, were used to help feed and unfeed the cables in sync with the rotation of the spools. Although stable flight of the sensor can be achieved using a single cable connected to the sensor near the center of gravity, we were concerned that the sensor would not remain perfectly in line with the opening at the bottom of the fuselage during retraction, increasing our risk of failure. This design also allowed us to suspend a heavier sensor, which adds to our score since we would not be concerned about the complexities with trying to retract a heavy sensor using a traditional rear cargo door. We also added 4 low-profile fins to the rear of the probe to increase the margin of stability. The deployment mechanism has a cross-sectional footprint of 2.5 by 3.5 inches, allowing us to fit up to 10 sensor shipping containers and store 300 inches of cable per spool, maximizing the score for mission 2 and 3 without having to increase the cross-sectional area of the fuselage and thus increasing the drag of the aircraft. For mission performance, we predicted a cruise speed of 69.4 feet per second, 101 feet per second, and 78 feet per second for mission 1, 2, and 3 respectively. Our all-up weight for each mission was 9 pounds for mission 1, 15 pounds for mission 2, and 13 pounds for mission 3. Without further ado, here is the full flight footage for the sensor mission. Although the clips you are about to see now are shown out of order, they were all filmed in the same flight, but due to competition rules, we had to edit everything to comply with AIAA's submission requirements.
Three, two, one. Gonna retract in 3, 2, 1. Alright, turning the lights on now. 3 LEDs cycling. Good. And lights turning off now. Taking off! Alright, I'll come around and start deploying. Deploying. All the way out. Lights on the next pass.
Yep. So you got lights now?
Yeah, go for it.
Lights are on.
Yeah, I see him. Yeah, I can see them, but alright, we need to go for retract soon, I think. I'll come around and start retracting. Retracting. It's coming up. Stopped it. Retracted. Alright, coming in for a landing.
We would like to give a special thanks to Will and Davis Aero Modelers for letting us fly there during COVID-19, and to our club advisor, Dr. Huang, for working with our school to give us access to the supplies we needed while our workspace was in lockdown. Most of what you see here has been assembled in garages, and for the most part we had to work hundreds of miles away from each other to put this all together. From the graduating seniors and officers of the club, thanks for the great times at DBF and at UC San Diego, and good luck next year.